Hi, I'm Ms. Hearn. Let's get started. This is part 2 of constructing power series for particular functions. In this video, we're going to talk about certain operations that work in general for power series and how we can use those to expand the types of functions that we can construct power series to represent. So for example, for the rules for operations that we're going to look at, let's let f of x be the power series a sub n x to the n and g of x be the power series b sub n x to the n, and k be a real number. Then, for example, we can plug in kx to the function f, and it's exactly what you would expect. You'd raise kx to the n power and you'd get k to the n x to the n, and the rest of the series would stay the same. And then we could plug in x to the capital N power to f, and exactly what you would think would happen. You're going to get x to the nn power. And then here we can add or subtract the two power series together, and all that's going to happen is thinking of them as a big long polynomial, right? You're just going to add and subtract the coefficients of the like terms. So you have a sub n plus or minus b sub n times x to the n. So for example, let's suppose that we wanted to add together the series n equals 0 to infinity of just x to the n with the series n equals 0 to infinity of x over 2 to the n. So we have to get them written in a format where the x to the n's are separate from the coefficients. So in this first series, the coefficients are just 1, but I'm just going to write that to emphasize that our a sub n is 1 in each case. Plus, we are adding to that, separating the x to the n from the 2 to the n. We're going to have 1 over 2 to the n times x to the n. So we can use property number 3 here, and we can just add the coefficients together, and we would have the sum n equals 0 to infinity of 1 plus 1 over 2 to the n x to the n. Right, so if we knew two functions that were equal to these two power series, we could use that fact to then get a new function to figure out what function is equal to the final sum of the two power series, and that's kind of what we're going to be doing. We do need to keep in mind that our intervals of convergence may change in this process. So for example, here, this first power series is it fits a geometric pattern where a is 1 and the radius is the absolute value of x. So this converges whenever the absolute value of x is less than 1, or in other words, it converges on the interval from -1 to 1. We talk about this in part 1 of this video series. And this guy over here, similarly, this is going to converge when the absolute value of x over 2 is less than 1, which means our absolute value of x is less than 2. So its interval of convergence is -2 to 2. But when you add them together, you can only, you're only going to have a defined function wherever both functions are defined. So that restricts you to the intersection of their two intervals of convergence. So if you take the interval of convergence -1 to 1 and see where it overlaps with the interval of convergence -2 to 2, you see that this final function will only be defined on the interval from -1 to +1. Okay, so we have a restricted interval of convergence here. So in the previous video, we constructed a power series for the function 1 over 1 minus x. We said that it fits the geometric series 1 times x to the n, centered at 0. And so I just wanted to mention that because of the second rule here that says you can plug in a power of x, that we could construct from our original function f of x, if I plug in x squared, I get 1 over 1 minus x squared. If I wanted a power series for this, I can just plug into that power series we already found here. And so this is going to be the sum n equals 0 to infinity of 1 times, and that's going to be x squared to the n. So this is the series n equals 0 to infinity of x to the 2n. So we've just expanded the types of functions that we can find power series for. So let's look at an example. We're going to find a power series for the function g of x equals 2 over 1 minus x squared, which is centered at c equals 0. So what I'm going to do is I'm going to consider in my solution the function f of x equals 2 over 1 minus x. I'm going to write that as a power series, and then I'm going to go ahead and adjust it for the x squared. So for f of x equals 2 over 1 minus x, our a is 2. What I should say is we're trying to match it up with our geometric series that converges to a over 1 minus r. So that means that a would be 2 and x would be r. And so what we're going to do is, first of all, make sure that we make a note that this is only going to converge here if the absolute value of r, in this case the absolute value of x, is less than 1. So we're going to have a center at 0 like we want, and we're going to have a radius of 1, radius of convergence of 1. So next we're going to construct our geometric series that has that quality. So it's going to go from n equals 0 to infinity of a times r to the n, which is the series n equals 0 to infinity of 2 times x to the n, which converges when the absolute value of x is less than 1. Alright, now our function g of x, which was 2 over 1 minus x squared, is exactly equal to f with x squared plugged into it. 2 over 1 minus x squared. So we are going to then plug x squared into the power series version of that function f. So we have n equals 0 to infinity 2 times x squared to the n power. Now of course that means that the absolute value of x squared must be less than 1. So this is going to be the sum, n equals 0 to infinity of 2x to the 2n. And our interval of convergence is going to be determined by the fact that x squared is less than 1. X squared is positive anyway, so I'm dropping the absolute value. This would mean that x squared minus 1 is less than 0. Well, x squared minus 1 equals 0 at negative 1 and 1. If we plug in a value in between and check it, we get a negative in between negative 1 and 1. Anything to the left of negative 1 or the right of 1 will give us a positive. So we see that x squared minus 1 is less than 0 on the interval from negative 1 to 1. So that's going to be our interval of convergence. So we wrote it as a power series and we found our interval of convergence. Now we're going to rework the same problem using a slightly different technique. Instead of plugging in x squared, using one of the properties, we're going to use the third property. We're going to break the function down into the sum of two functions using partial fractions. Same function, and we're going to come to the same conclusion, but just using a different technique. There are lots of different ways to do this, so we're just trying to kind of build up all the tools in our toolbox. So alternatively, what we're going to do is we're going to analyze 2 over 1 minus x squared, this time different solution, and we're going to break it up into, well, remember 1 minus x squared factors into 1 minus x, 1 plus x, which are both linear. So we're going to write this as a over 1 minus x plus b over 1 plus x. And so our characteristic equation that we're going to have is 2 equals a times 1 plus x plus b times 1 minus x. And so if x were negative 1 in this equation, we would get 2 equals 2b, which means b is equal to 1. And if x were equal to 1, we would get 2 is equal to 2a, so that would mean a is equal to 1. So we see that 2 over 1 minus x squared is equal to 1 over 1 minus x plus 1 over 1 plus x. So we have a sum here of two separate functions. I'm going to write each of them as a power series. So how do I do that? Well, remember, we're always trying to match this up to a over 1 minus r, so we can use a geometric series. For the first function, 1 over 1 minus x, we would need r to just be x. For the second function, though, this would be 1 minus negative x, so r would actually be equal to negative x. So our power series representations of these two would be the sum. A is 1, by the way, in both cases. So that would be the sum n equals 0 to infinity. We don't need to write the 1 for the a. We're just going to have x to the n plus the sum n equals 0 to infinity of negative x to the n. Or you could write that as the sum n equals 0 to infinity of 1 times x to the n plus the sum n equals 0 to infinity of negative 1 to the n x to the n. So adding the coefficients here, remember these act just like big long polynomials, this is going to be the sum n equals 0 to infinity of 1 plus negative 1 to the n times x to the n. Now whenever you have 1 being added to powers of negative 1, something where at various terms that they're going to cancel out, it's probably a good idea to write out the terms of the series and see if anything's going to maybe collapse. And so that's what we're going to do now. So we're going to write this as, let's see, when n is 0, we would have 1 plus negative 1 to the 0 is 1. And then we would be multiplying times x to the 0. And then plus the second term when n is 1, we would have 1 minus 1, which is going to be 0 times x to the first, plus when n is 2, we're going to have 1 plus negative 1 squared, so we're going to have 1 plus 1 again, or 2, times x squared. And this is going to keep happening as we go through the terms. The odd powers will result in a 0 term, so 0x cubed, and the even powers are going to result in a 1 plus 1 coefficient. So what we have is we have 2 plus 2x squared plus 2x to the fourth plus 2x to the sixth, and so on. So how would you write that as a series? Well, that's going to be, let me write in different colors so you can see where it stands out up here. So this is going to be the sum n equals 0 to infinity of 2x to the 2n. Now remember, we already found a geometric series representation of this function, and that was back here. And remember, it was exactly 2x to the 2n. So by using this different technique, we're still coming to the same conclusion. We should note the interval of convergence. So the interval of convergence for the first part of the function would have to be negative 1 to 1, because we need the absolute value of x to be less than 1. And it would also be negative 1 to 1 for the second function that we added to it, because again, the absolute value of negative x would need to be less than 1 to guarantee convergence. So we would still come to the conclusion that the interval of convergence is negative 1 to 1. So that's how we would use partial fractions to write the power series for this function centered at 0. So that concludes part 2 of the series on constructing power series for particular functions. In the next video, part 3, we're going to look at using a power series to construct another power series. I hope you found this video useful. If you did, please remember to like it. That helps other students to find the video.